Hello, everybody, and thank you for joining us for our presentation about how counterfactuals are used to overcome data bias and increase the model fairness. My name is Stefanake Cornell, and I'm the CTO of Assencor and lead researcher in AC Labs. I have a PhD in applied AI in manufacturing, and today's study was performed over a period of 6 months in our internal department called Assencor Labs, which is a research department. Why we did this? We at Assencor, we focus on ethics, responsible AI, and fair predictive models. Since all AI models learn from human-created data set and behavior, there is a high risk that data bias will be captured. For some dataset, there is an easy way to identify such bias through simple data science, but when the bias is encoded in multiple features, then identifying this through simple analysis is almost impossible. Today's presentation will have 3 parts. First will be to explain the algorithm that we applied in order to reduce this bias. The second part will present the results, and the last part will showcase the tools that we've built in order to perform the research. Just a reminder, you can always use the chat window to ask any questions or clarifications, and we are going to address the questions as soon as possible, in context or at the end of the presentation. Next, I will let my colleague Sarah to present herself and go into more details about our approach.
Hello everyone, I'm Sarah Vishavan and I'm a machine learning engineer at Assencor, where I'm currently working on the research side within the AC Lab department. I have a bachelor degree in computer science and working on taking my master degree in AI being my passion. And I will present to you the research that Cornell and I worked on within AC Lab's department, and which we entitled Using Counterfactuals to Overcome Data Bias and Increase Model Fairness. Next, we have a brief content, an introduction, a couple of use cases, the data set, the model, how we explain a model, what is our goal, the heuristic we are using to reach our goal, what is a counterfactual, how we generate these counterfactuals for different data sets, what is our model that we proposed for the problem that we found, and our scientific paper. So as an introduction, we know that machine learning services and AI services are used in critical tasks like medical diagnosis, self-driving cars, online fraud detection, financial services, and so on. And for a user to use these services, we first have to make them be trustworthy. So a new concept was introduced in the artificial intelligence field called explainable artificial intelligence. And this seeks to explain why a service took a decision. And later on, we are going to use this concept to prove the fragility of these services and then how we solve this fragility. Next, we have a couple of use cases. The first use case is when we are going to a bank and request a loan. So here we have an individual with the following attributes: an income of $2,000 per month, gender male, and has a bachelor degree. And the AI system decides that this individual should not receive the loan. Below, we have an individual that has almost the same attributes, but has an income $2 more. And for this individual, the AI system decides that this one should receive the loan. So we see that the AI system that the bank is using, it's fragile. Just by adding $2 more, the decision is different. In a second use case, Um, we have an insurer that wants to find out the risk class in order to calculate an insurance price. Here we have an individual that is a 40-year-old female and owns a car that is red. And the AI system decides that this individual has a high risk. Below, we have an individual with almost the same attributes, but the color of the car is blue. And for this one, the AI system decides that the risk class is low. So just because the color changed. So the color property of the car is directly influencing the decision of the system. And this is not an honest judgment. Just because this model was trained on a data set that contained a greater number of accidents that involved red cars. So,
So usually what we've tried to capture is the amount of information diversity. We try to fix that if the data set doesn't contain information that diversity, it will be prone to make unfair decisions. So taking this last example about the car insurance company, if for an insurance company, all the red cars have been involved in a car accident, the AI will learn that most likely if you own a red car, then you will be involved in a car accident. Our solution will tries to reduce this bias toward the color red that when the AI is making the decision.
yes, so we are trying to get rid of this model fragility and the biases. In this case, the color of the car is a bias in the data set. Next, we are going to use a data set to exemplify the process better. A data set is composed of attributes and sometimes an output. And we took the adult income data set, and this data set has the following attributes. We have age that has to take values between 17 and 90. We have work class that has to take between these values, never worked, private, without pay. We have a final weight score that is an aggregated score calculated based on some of the attributes. We have education, so the individual could have a bachelor degree, a PhD, finished a high school or a master. We have the education number that tells us the years spent in school. We have the marital status. It could be divorced, married, never married, occupation, relationship, race, gender, hours worked per week, and native country. Also, the adult income data set has an output. Here is the salary status that can be greater than 50,000 or less or equal to 50,000. And this data set contains 32,000 samples in total. And below we have two examples. Here we have an example that is classified in the data set as having a salary greater than 50,000. So here we have an individual that is 42, work class private, has a bachelor degree, is married, husband, white, male, works 40 hours per week, and is from United States. On the right, we have a sample that is classified in the data set as having a salary less or equal to 50,000. We have a 32-year-old male, white, that is unmarried, finished high school, works 40 hours per week, and is from United States. And next, after we have our data set, we have to develop and choose a model that learns our data set, that learns hidden patterns and relationship in our data set, and train our model on the data set. And after the training, our model gives us an accuracy that tells us how well the model learned the data. And we have to make sure that this accuracy is high, both for the data that he learned from and from unseen data too, because we want our trained model to generalize well, so we can use it further on unseen data. We will see further. Also, the model outputs a feature importance graph that we can see here, and this tells us which features were the most important for the model to make the salary decision, whether it is greater than 50,000 or less or equal to 50,000. And we see here that for the model, the education number is the most important. Then we have the marital status, the age, the hours worked per week. And how I said, the model that we trained, we can now use it to classify new samples. Here we have a never seen sample by the model. We have here a 34-year-old female that has a PhD, is divorced, works in sales, it's white, works 50 hours per week, and is from United States. And the model classifies this sample as having a salary less or equal to 50,000. And
I would like to add one interesting fact that we discovered during our research is that a strange bias was captured in the data set, because if a row would have been gender female, but the marital status would have been divorced, then it would be more likely that the outcome would be more than 50K per year. Now, that was an interesting aspect that was captured having an aggregate set of features, not a single feature that influences the decision, such as origin.
yes. So next, after we have our trained model, we ask ourselves what should we change in the individual's attributes so the model predicts that this sample has a salary greater than 50,000. And we want to explain this to that individual by identifying the smallest amount of changes that we have to do in the attributes capable of changing the initial prediction of the model, to change the prediction for less or equal to 50,000 to greater than 50,000. And we use a heuristic to generate potential solutions. So our goal is to identify the smallest amount of changes so the model predicts a different outcome. And this is called the counterfactual. Below we have an example of a counterfactual generated for this sample. So we have a 25-year-old male from US, and our trained model classifies this sample as having a salary less or equal to 50,000. Next, we are going to use an algorithm that we developed to find a counterfactual, and this is what the algorithm returns. So here we have a sample, 25-year-old female from US, and our trained model says that this sample now has a salary greater than 50,000. So we see that we changed the gender and the model decision changed. So our model the model that we are using prefers a certain gender. So our model is gender biased. Next, I'm going to exemplify the algorithm that we are using. And for the input, we need one sample data that we want to explain. And we have three variables: generations, population size, and replace. We start with the first generation of the 200, and we are at step 0, where we choose the sample that we want to explain. Here we have a 34-year-old female that is white, has a PhD, divorced, works in sales, works 50 hours per week from United States, and we want to see what our trained model says that for this sample, what is the salary. And for this sample, the model predicts the salary less or equal to 50,000. And we want to find a counterfactual. So in step one, we generate 300 random samples, and each of these sample looks like the one from step zero, just that they're having different values. So we have here an individual that is not 34, it's 35.
But the random, the initial population that is generated is rather far from the solution that we're searching, from the neighborhood where we're searching the solution, such that we allow the algorithm to find that to
Global.
find solution, yeah, the global optimum for the searching domain. The searching domain for this particular problem is huge. I think we've calculated it. So doing a using classic methods such as searching with a for, it will take forever to find a counterfactual and parse through the entire searching domain.
Yes. In step two, we calculate a fitness score for every sample, and as close as is the closer the generated sample is to the input sample, and by closer I mean that there are small changes between them, then the fitness score is going to be small. And also we have to see what our training model classifies the salary for each sample. So if we have for this sample a salary like greater than 50,000, then we keep the fitness score as it is. But if the salary is the same as for the input sample, if it's less or equal to 50,000, then we are going to penalize the fitness score with a larger value. Because we are searching for a counterfactual has a different outcome. In step three, we are keeping the 10 samples that have the smallest fitness score, and with the 290 remaining samples, we go in step four and make a crossover mutation operation. We take samples two by two, and for the crossover operation, we split the samples by a random position, and after that, we interchange them. In the mutation operation, we iterate through each feature and change it with a certain probability. In step five, we take the 10 samples that had the smallest fitness score and concatenate them with the new generated samples, the 290 new samples, and now we have the population for the next generation. And in step six, after the 200 generation, we get the sample that has the smallest fitness score, and that is the closest sample to the input sample, the counterfactual.
I would like to add something here. A big challenge that we had during this development was the calculation of the fitness score. Since we're searching for the minimum amount of changes that need to happen in order to change the outcome, and we are having both continuous and categorical values. And when I'm saying continuous, I'm thinking something like hours per week because it's from 1 in 90 hours per week or things like that. But we also have categorical,
The
such as
gender.
yeah, such as gender, region, or marital status. But a change from 40 hours per week to 45, it's a magnitude of 5 units. But a change from divorced to married is of magnitude of 1. What we did is had all the continuous valued features mapped on a domain from between 0 and 1, and had change the the change the changes calculated on this domain, and we've considered that a categorical change will be of a magnitude of 1.
Yes, and next we can see two results. We have the first result, so we have here the input sample, that is classified by the trained model as having a salary less or equal to 50,000. We have a 35-year-old female that is white, has a PhD, is the same input sample, and this is the counterfactual that our algorithm returns. So the model says that now the salary is greater than 50,000, and we see that we have here change for the gender. So the model that we are using is gender biased, prefers a certain gender. In the next result, we have this input sample. We have a 33-year-old male husband, has 12 years spent in school from Germany, and he works 45 hours per week. And this is the counterfactual that our algorithm outputs. So we have here 46 hours per week. So we added just 1 hour to the hours worked per week, and the model's decision changed. And this is not a corner case in which the individual had a salary equal to 50,000. So the model that we are using here is fragile. Just by adding 1 hour, the model decision changed.
So we tried to capture such solutions because think about it, if you go to get a loan and for some reason your loan is denied, and part of that decision was taken by an algorithm, and you would ask why, what's the reason that I have been my application was denied. Think about if you are a human, you would more likely start to change something like income or hours per week, as we see here, but you don't actually see the reason why the algorithm took that decision. Think about when you're having complex neural nets that are part of the decision. It's almost impossible to look into the internals of what the neural net learned such that you can backtrack back to the decision. So with our solution, we can capture the closest value that is not part of the initial data set that would
Yes.
change your outcome.
And next, we have a data set that is composed of images to see how we generate counterfactual for this type of data set. And we took the MNIST data set, and how I said, this is composed of images, and each image is labeled with the number that is represented in the image. After we have the data set, we have to develop to choose a method that learns our data, outputs an accuracy that we have to make sure it's a good accuracy. And after that, we can classify new unseen data. Below we have two images that were drawn by us. So we have here two, and to avoid confusion, the white squares are the black background, and the black ones are the white pixels. So for this image, we enter this image in the trained model, and it classifies this image as a 2. So it's correct. We have here a 5, and the model says also that this image is a 5. And next, we ask ourselves what changes, what are the smallest amount of changes that we have to bring to this image for the model to predict this image as a 7. And this is the result. So for the trained model, this image is a 7. Here we have second result, we have this 5. The model says it's a 5, but we want to see what are the smallest amount of changes that we have to bring to this image for the model to say that this image is a 6. And this is the result. So we see with our eyes that this is still a 2 and this is still a 5. So next, this is our solution to correct the data set. We want the data set to be well defined and with no hidden biases. So what we are doing, we take the generated counterfactuals and we label them correctly. So we say that this image is a 2 and this image is a 5. And we add them to the initial data set and give this data set for the model to learn hidden patterns and learn that this is a 2 and this is a 5.
There is one
And
important aspect here is that we do not allow all the generated counterfactuals to be placed back into the data set. We for each data set we have set a threshold of the amount of changes that need to happen. Uh, need actually we the amount of changes should be less than a threshold. So if there are for this example, if there are less than 5 pixels changed, then that's a solution. But if the number of changes, if it generates a noise, just a noisy data, and classifier, I don't know, classifies it as something different, it will not be selected to be placed back into the data set because the generated solution is very different from the original input. If you want to try it, there is a running sample on our website. If you go to our AC Labs page, you will find a MNIST counterfactual generator that you can draw your own numbers and try to find counterfactuals. It's really fun. You should check it out.
yes, and next we have our scientific paper that contains our research, the method in detail, and an experiment that I'm going to exemplify further on. And as Cornell said, on our website you can get our paper also in the ASECOR Lab section. And next, for the experiment, we used a modified adult income data set that we handpicked in order to favor a single gender. So in the graph, we see the difference in the number of samples between genders classified with a salary income less or equal to 50,000. And this is the difference between the number of samples between gender that is classified with a salary income greater than 15,000. Next, we see the influence of each feature on the outcome. So we see here that gender has the biggest decision-making factor on the salary outcome, and we aim to reduce this bias that is present in the dataset. So we have here a debias process that we start by taking 1,000 samples, and for each sample we generate one counterfactual. We are in the iteration 1, and for the 1,000 counterfactuals generated, we have just 658 accepted counterfactual. So for a counterfactual to be accepted, should not exceed more than 2 changes. So 2 changes would be, one change would be the change in gender, and another change adding 1 hour to the hours worked per week. And with the accepted counterfactuals, we take them, add them into our data set, take the data set and retrain the model with the new data set. We go in iteration 2 with the retrained model. We take the same 1,000 samples, generate counterfactuals, and in iteration 2, we have just 579 accepted counterfactuals. We add them into the data set and retrain the model. And we see that as the number of iterations increases, the number of accepted counterfactuals is smaller and smaller. So we find solutions harder and harder. The number of changes exceeds the threshold 2. So our model is it's more robust. And after each iteration, we extracted the number of times we changed the feature for the generated solutions and for the accepted solutions. And we see here that the gender was changed the most in generated and also in the accepted solutions, accepted counterfactuals. And in the last iteration, the seventh, we see that the number of changes on the gender for the generated and also for the accepted decreased, and the focus shifted on the other features that are more relevant in real life, like education number, age, hours worked per week. But we can observe that the accepted counterfactuals are also small because the counterfactual exceeded that threshold, the 2 threshold. And after this debias process, we can see for the initial data set and for the final data set how the influence of the feature on the outcome on the salary has changed. We see that we have here a drop for the gender, and we wanted to make sure that by doing this, we will not significantly influence the rest of the features. So here are the results. Here in the education number decreased a bit, but the rest stayed almost the same.
So what was really important for us is to have this set of features like education or age still have a big influence on the actual outcome, because we do consider that real life decision making features should be preserved. Something like gender, race should not be part of a big decision. Sometimes they might be, but they should not influence.
Yes, and next Cornell is going to present the tool that we use to make this experiment.
So actually, we never intended to develop a tool
Yes.
that is going to be used. So we wanted to develop it to use it internally, so it would ease our life. But the good news is that currently helped us a lot in accelerating the research. So we are planning to release it as soon as possible as a beta version. It will be an open source product. We are still trying to find a good name for it. Today is called ML Blocks. I'm going to switch the presentation to another window. It is basically a data pipeline that will allow you to encode any machine learning, AI, or reporting features. So as you can see here, each of the squares that you have here have a different responsibility. They can easily be customized both in code before getting them into the runtime environment, but they can also be customized at runtime. What is really important is that everything that you will see as an UI for interacting with the actual block, it is generated. So there is no UI coded in the behavior of the application. Let me give you a really simple example. So we have a block that does nothing. It is just a root element in our use case. And we have two different blocks. We have a data transformation block and a data exploration block. How it's working, you can select one of the blocks here. And if you go, let's say, and we're going to upload the adult data set that we used for our research, you will see that at this point, all the data is propagated on the downstream blocks. So if we are going to explore the AI root block and we explore the data, you will see all the features that were presented by my colleague listed here. Down the line, we have this data transformation block, which its responsibility is to filter or to remove some of the columns. We have a settings. As you can see here, I'm setting this up to remove the capital gain and gender columns. So as you can see, capital gain and gender are missing from my data set. You might have already guessed gender was a mistake here because I wanted to have capital loss removed. What is really, this is where I want to highlight the flexibility of this tool. So we do not care about the data that was uploaded upstream or the data that is held by this block, and the columns to remove are depending on the data that was uploaded. So everything is dynamic. There is no need for you to code the list of features that are here. So what I'm going to do, I'm going to save the changes, and of course there is no change in the data, but I can always go and say, okay, rebuild my block, and you can see it will fetch the data from upstream. And if I'm going to go into the explore the data, as you can see here, I am missing the capital gain and capital loss. Moving forward to the next block, which is a data exploration block. As you might have guessed, if I'm going to see the data, I still have the capital gain and capital loss columns because it is downstream to explainable AI route. But what this block does is perform the basic data analysis of the uploaded data set. So there is going to be a PDF that is generated, which contain the correlation matrix, the value distribution for each column. Later, there are some analysis that you can take some decisions on removing some of the outliers. What else? So we perform each of the analysis for, we perform this analysis for each column. So this would be really easy to have a preliminary analysis of the data. What I would like to highlight. So if at this point I'm going to take this block and say, okay, you are no longer dependent on the explainable AI route, but I want to make you dependent on the data transformation block. You can easily go and say, okay, you are now part downstream to the data transformation. So if I'm going to rebuild this, you will see that the data transformation is going to get and fetch the data. What happens here is that the current block that I'm having is going to miss the capital gain and capital loss columns because it is taking the data from upstream. So it's a classic data pipeline. The most probably the static, the analysis hasn't been performed yet, but as you can see here, it already started to generate the static resources. So I have the correlation matrix already computed, and as you can see here, the capital gain and capital loss is missing. So this is the pipeline. This is the basic functionality of it. But in order to enable our research, we have this Keras classifier, which is a basic neural net dense Keras classifier that can be set up at runtime. So you can input the number of iterations that will be run in training, the batch size, the optimizer, and since we are having Um, Categorical decision, we're going to use the loss functions for sparse categorical. Also, the layers can be set up, and we have two units for outcome. One is greater and one is lower than 50K, but can be changed at runtime. Uh, Usually you can, I have removed it from my initial pipeline because in order to do this demo, I wouldn't want it to have the classifier to get retrained, because with each data change from upstream, then the model training will be triggered. So whenever there is new data, the model will get retrained. Otherwise, if we interrupt the connection, if we remove the connection between the blocks, then the retrain will not happen. So we do want to plan to have a scraper that for an AI to learn something from the internet, but that's for this topic is for another presentation. So this Keras classifier, what it can do, it will have this predict tab where we take this UI is generated based on the data that the model the block holds. So let's say that we have a 25-year-old that is working in private sector, master's degree, so this would be like 14. So it works in sales, is a white person, gender male, and works 25 hours per week. I'm going to go to the model and say predict immediately, because it can run the prediction asynchronous. So as you can see here, the result is 0. This means that the features that I've inputted here, my neural net decided that is less than 50K. So the question would be, what do I need to change to this outcome such that, to these features, such that the model to predict something different? As a human being, most probably I would go, let's say 50, work more. Hopefully, now I'm still getting a less than 50K, so it's really hard for me to find that solution which is close to the initial one. So, but we have this explain decision block. The actual algorithm, the block that holds the algorithm that Sarah presented. So what we're going to use it for, let's say, okay, use the upstream Keras classifier and its trained neural net to find a counterfactual. We have used it for MNIST as well. You can use it for any predictive model. We don't care. So we use it for CIFAR, we use it for MNIST, and also categorical data. The advantage of this tool is that standardize the communication between such blocks. Each of these blocks is a separate container that runs in an isolated network. So data corruption is almost impossible. So we're going to try to find a counterfactual that will run on the Keras classifier. We're not going to target the class. We're going to say just change the class. This is population count. Let's say that we're going to have multiple mutation point. We're not going to push it back into the data set because this will trigger retraining. And we're going to, okay, let's say that we do want to have the differences printed out as a static resource for my 25 years of old person that is working in the private sector, masters, let's say 14, occupation was in sales, was white, male, and it was working, let's say 40 hours a week. So at this point, I'm going to submit, and you will see that the block already started working with the Keras classifier in order to find a different solution to what I have inputted. So I will go to my block and explore the static resources. And hopefully this is the one. Yeah, I have the 25-year-old white male that in order to change my outcome will have to be a 25-year-old white female. So there is still, even though that we reduce that bias towards the gender, there is still a little bit of bias in gender change. This solution would have not been accepted to be pushed back into the dataset because the number of changes is the magnitude of changes unit is 3 units. It changes three features. So we have a change in age, we have a change in gender, and there is any other. Should be one. Oh, so we have the 25 to 27 and as a female. So we can come up with this block outputs different information such as how fast the solution was found. For more complex data sets such as the MNIST, you will see that the solution finding is really slow. So, but for this one, it's really easy to find the solution in the neighborhood. Yeah, so for my 27 female, if I'm going to submit again, I will tell to my counterfactual, okay, find me another solution to my to the one that you found. So you can play with it as you wish. So we're going to go here, look into the statistics, and apparently that it was really easy to find that the model decided that a single change in the gender would be a different change. We'd have a different outcome. So this is this will exemplifies that our model is still fragile and it still have some bias encoded in the gender. So this is the tool at this point where we are reworking some of the internals. We want to enable more solutions for the data storage because currently it is using an internal database, but we do want to hook it to other databases out there. One important thing that we are currently working on is to move a model from one block to another. So we can have as many Keras classifier as we wish, and we can describe different pipelines. We can describe a production, EQA, and the development pipeline. Let's say that this tool can be used for anonymizing data for the development pipeline. But then you would publish the model to the QA pipeline and publish the model structure to the QA pipeline and retrain it and see if it works, even though the developers don't have access to the anonymized data. But then if the QA pipeline measurements are more accurate than the production pipeline, we do not need to retrain the model. We just move the train model from one block to the other. So the QA block will become as part of the production pipeline, and the production block will be part of the QA pipeline. So we just make a switch. This is pretty much it. Hopefully, we're going to be able to have more research soon. If there are any, we finished our presentation. If there are any other questions, you can address them now in the chat window, or you can use any other channel for communicating with us. Our emails, you can connect with us on LinkedIn, you can follow our page. We started a new research, which is really exciting. We're trying to model how our uh, brains are holding context and try to create a better light language model. But we're at the beginning. Still, we have exciting results. So thank you. If there are no questions, looking forward to be seeing you at our next presentation.